Log on, tune in, find out. Another good idea from Cambridge.
The Sanger. So to set the scene a little bit for this work, this has been one part of a collaboration that I've been involved with the Twins Research Department at King's College London. So for about the last 15 years, they've been running the Twins UK Adult Twins Registry, which includes around 12,000 female Caucasian twins from across the UK. Typically, they've visited St Thomas's Hospital in London, where the department is based, every kind of 3 to 5 years. And when they visited, they've had a range of clinical measurements taken by nurses and doctors. And they've also often filled out kind of postal surveys to get some extra information on the lifestyles of these individuals. So there's really rich clinical data that we have for 15 years of these 12,000 individuals' lives. And more recently, there's been a Wellcome Trust funded project called MOTHER, which stands for the Multiple Tissue Human Expression Resource. And that's basically provided funding for gene expression microarrays in 3 different tissues in a subset of 900 of these individuals, and also for SNP arrays, DNA sequencing, methylation data, and small RNA data. So on these 900 individuals, we have a really amazing depth of information. The bit I've been particularly involved with is looking at the clinical data on these individuals. And there's been kind of a lot of there are a lot of statistical issues with this data, although it's clearly we'd like to get a lot of use out of it. There's a lot of missingness, it's very heterogeneous, and this kind of thing. I'm going to talk about one specific sub-project, because I have 10 minutes and counting, which has been this idea of trying to infer an individual's physiological age. So obviously we know the individual's chronological age, assuming the data has been stored reasonably well. So intuitively, the idea here is I'd like to be able to look at an individual in terms of some set of clinical variables. In this case, I'm actually using these variables. And imagining I didn't know their chronological age, I'd like to have my best guess of what their physiological age is. So my best guess of what their age would be. And I think the nice thing about this is it's a very intuitive idea. You can explain this to anyone on the street and they'll kind of understand what you're doing. So how are we actually going to try and do this? Well, I'm going to start off using the simplest linear model I could think of to do this. So here, let me explain this equation. So the y is an observed phenotype, an observed clinical variable. The subscript n is which individual I'm talking about. The subscript d is which phenotype I'm talking about. B is some slope for the regression, which I'm going to learn. C is some intercept. E is some noise. A is just the known chronological age. And the interesting bit here is this delta. So delta is some little adjustment I'm allowed to make to an individual's chronological age. You can think of it as input noise, maybe. But the important point about delta is that it's shared across all the phenotypes I'm going to look at for this individual. So I'm saying across all these phenotypes, if I was allowed to make a little adjustment to this person's age, what adjustment would I make to explain all those variables a little bit better? I'm going to fit all the parameters in this model using a variational Bayes approximation and using some software called Infer.net, which is Microsoft Research software that I actually do some work developing. And you can, for the statisticians in the audience, you can think of Infer.net as kind of WinBugs for variational methods. So the collaborator we have at King's is a doctor. He's a clinician. He knows some statistics, but not very much. So it's really nice to have a simple explanation of kind of roughly what our model is doing. So that's what I'm trying to do here. So this is one particular clinical variable I'm looking at, lens nuclear dip, which is basically a measure of how bad are your cataracts. And this plot shows for the individuals, the kind of 6,000 individuals I'm looking at in this study, how the lens nuclear dip varies with age on the x-axis. And I put the line of best fit on here. So let's take one particular individual, this 55-year-old lady. Now she has a pretty bad lens nuclear dip for her age, because the expected value for her age would be down here. So I could say that this 55-year-old individual actually has the lens nuclear dip of a 79-year-old. So the delta in my model would be plus 24. So if I just look at her cataracts, it seems like she's 24 years older than her chronological age. Of course, that's just one variable, and this might be just noise, or it might not correlate with anything else in the data set. So we could look at the same individual for a different variable, say telomere length, which we also have measurements of, and here her delta would come out as 17. And our model is basically, you can think of as a smart way of averaging these different deltas across different phenotypes. Some quick results. So the top row here is showing lens nuclear dip again. And on the left, I'm plotting lens nuclear dip against chronological age. And on the right, I'm plotting against this learnt biological age. And what you basically see is that the correlation becomes stronger, which is what I would expect to see, right? That if I correlate to true physiological age, then the correlation will be stronger than to chronological age. One problem we found is that often these dependencies on age don't really look linear. They look non-linear. And so you get effects where the delta that we learn is coming more from trying to compensate for the non-linear effect of age on these clinical variables rather than modeling what we want, which is systematic aging across this set of variables. So to try and account for that, we're now using a non-linear model, which is, I don't want to go into the details of this too much, but basically it's a mixture of linear experts, where which expert I'm in, so which cluster assignment I'm in, comes from a multinomial logistic regression model. So the interesting thing to do with this, I think, is to see whether I can correlate more effectively to physiological age rather than chronological age when I look at the gene expression data that I have. And that's something that we've started doing here. So this is specifically work that Leo Part at the Sanger has been doing, and Jihao is in the audience is continuing with, which is to look at how many, for a fixed false discovery rate, how many genes correlate to chronological age and to this physiological age from the model. And basically what we see is when I look at physiological age, I get quite a lot more associations with the gene expression data than I do just looking at chronological age, which is some biological confirmation that we're doing something sensible and something meaningful. So a few things we've talked about for future work. When you talk to biologists about this, they say, well, that's a nice idea, but it's probably not really what happens. So what really happens is there'll be different organ systems in the body that are aging at different speeds. And it would make more sense to have some kind of idea of multi-dimensional aging. So you have a different age for different body systems. And then you could also, that might be more interpretable and more, because when you look for associations in gene expression, say, you would expect to see associations to relevant genes for that particular organ system. We're also not using an individual time series data at the moment. We're just looking at one time slice. And what we'd really like to move towards is using more of the data that we have on this set of individuals. So at the moment we're using gene expression and clinical data, but we'd really like to also incorporate the genotype data that we have as well. That's something we're starting to look at. Okay, thank you.
We're well within the 10 minutes there, so plenty of time for a question or two.
Do you do a linear regression for each of the genes on the whole genome?
No. So the linear regression. So the data I'm learning this from is just the clinical data, and then when we go to associate when we go to associate to the gene expression data, we do that as a secondary step, and then yes, it's a linear mixed model to get the association for each gene. But we do that as a separate step.
Have you thought about maybe accounting for the dependence among genes?
Yes. So if you talk to GHAL, there's lots of things we're doing to do that. So there's been quite a lot of work. So the collaboration between Microsoft Research and Sanger, which Richard's been heavily involved with, they've done a lot of work. So they have this software in R called PEER, which is basically a kind of really robust factor analysis model to remove dependency from genes in a gene expression data set. So the idea is if there's technical confounders and this kind of thing, then you expect to see a very broad effect across a lot of genes. And if you remove that effect, then you can find stronger associations to whatever you might want to find associations to. Martin?
Do you know if age should be additive, this adjustment to age, should it be additive or multiplicative? Because maybe I have a different rate of aging or something.
Yeah, no, that's a good point. And something that I think, especially if you're looking at the time series modeling, then it's an interesting question, right? Like, it doesn't seem to make sense to give an additive adjustment across your entire lifespan. You certainly think that as you get older, there could be a bigger spread. And actually, I mean, I see that in the data set. So if you look at the older individuals, I get a bigger variance of delta than I do for younger individuals.
Okay, I think we'd better move on to our final speaker for the session.